Okay, so now we proceed on this course by discussing damage at higher doses and over long time scales. So in brief, to illustrate what we are talking about in this lecture, I'll come back to this schematic which has also been used previous on this course. So far in the course, we have mainly been discussing the primary damage, which is basically the top part of this. We have the collision cascade, the heat spike effects, and then we say that there is a number of damage left after the heat spike, which was discussed and described, for instance, with this ArcDPA and RPA models. But now this here is in many ways very limited because obviously when you do something on a macroscopic scale, 100 picoseconds is an extremely short time. And if you irradiate something for hours, you realize that what happens on 100 picoseconds may not be so relevant after you've been repeating this for hours. And to give an illustration of what can happen after this primary damage state, we will discuss all of these effects illustrated on the bottom part of this schematic in basically the end of the course. In this section 8, we are discussing defect mobility and also partly high dose effects, what happens when damage is overlapping. And then in the next section, we are discussing dislocations, which are in metals the key outcome of irradiation and also sometimes important in semiconductors and ionic materials. And because all of this is discussed in detail, I won't go into the details of the schematic at this stage anymore. This is mainly as a reminder of what will be discussed. Section 10 of the course then will deal with the practical applications of irradiation, which in most cases are related to these higher dose, longer time scale effects for the obvious reasons that macroscopic effects come on macroscopic time scales. So to start, what happens after a primary damage effect? So we told that, okay, we have the remaining primary damage, single vacancies, single interstitials, and sometimes small vacancy clusters, interstitial clusters, sometimes, as we mentioned, dislocations or amorphous zones as well directly from the irradiation. But what happens after this? After about 100 picoseconds, the system has cooled down to the equilibrium temperature, which may be room temperature, maybe liquid nitrogen temperature, 77 kelvins, or any other temperature in principle. And at this temperature, then regular thermodynamic diffusion effects start being active. For instance, an interstitial very often is mobile, and if it's mobile, it will start migrating and moving around, and it may move around. It may, if there is a vacancy nearby, it's very likely it will find the vacancy, recombine with the vacancy, and then instead of having a vacancy and an interstitial, you are left with no damage at all from this pair, and so on. So you realize that the outcome may be dramatically affected by this longer term migration. It's not always. Sometimes the long time scale effects are surprisingly small, and we'll also mention examples of that. So we'll go on from discussing this primary damage into this long-term evolution. So this is what I already mentioned, we have these long-term migration processes. You can have many kinds of clustering processes and so on. The other thing which may happen is that after a while, you may have another collision cascade in the same region. Then one will create new defects here, and these new defects may obviously be affected by what defects already existed there, but they can also recombine the pre-existing defects. This effect of new cascades overlapping regions with previous damage is called damage overlap. This will also be discussed in this section of the lecture notes to some degree of detail. But one important thing is to keep in mind is that almost all typical irradiation fluxes, the damage creation between the damage creation events is of the order of microseconds to seconds. If you take a typical ion beam flux, you get this kind of numbers. If you take a neutron flux, typical neutron flux, it's much lower. And you realize that if you compare the 100 picoseconds, which is damage overlap time, you realize that a lot of things may be going on, and all of the defects may very well have vanished before you hit the region with a new cascade. And here is now an illustration and computer simulation. This is not fully realistic as a simulation condition, but within the limitations, it is realistic and should give an idea of what's going on here. So what was done here? This is a simulation of a low energy cascade at 3 kV gold, recoiling gold at 600 kelvins. And this will show the collision cascade pretty much as usual. But importantly, this plotting is now of all atoms in this cubic cell. And this is a pretty small cell intentionally, that less than 100,000 atoms. But you can see this means that you are not missing any interstitial-like defect will be visible between the lattice planes. But then on the right-hand side, we have also used Wigner-Seitz defect analysis to analyze what defects are actually present here. And this will illustrate what happens. In this initial stage, the recoiling atom, this has analysis has started when the atom already started moving, so the recoiling atom is initially visible here as a defect, but otherwise nothing is seen because it's all perfect crystal. Now you see a typical collision cascade. These are the damage energies, but here we are plotting only defects, so that blue is the vacancies, red is the interstitials in a Wigner-Seitz defect analysis. So now you see that you have the heat spike, which is exists for a while, but after a while, as for reasons described earlier, the heat spike vanishes and you are left with only a few defects. And now looking at the right side, you see that you have actually, after a while, you had only 3 interstitials and 3 vacancies, but eventually everything vanishes. Now this is slightly artificial because the reason is that we use periodic boundary conditions also in the migration stage. So in reality, it would be perfectly possible that the interstitial, which is migrating more rapidly, would have escaped and gone somewhere far away and then not recombined. But this is to illustrate the point that you may have recombination effects. Also, it might have been the interstitial would have found a vacancy from another recoil cascade event and then recombined somewhere further away. But anyway, this also illustrates the time scale. Note that the time scale in this plotting was highly changing. In the beginning, the time scale was very short, but in the end, this simulation proceeded until 6,000 picoseconds, 6 nanoseconds, which is way longer time than the about 10 picosecond of the cascade. To appreciate this, I'll rerun this animation, but now ask you to take a look only at the right side of this animation here. So now we have the heat spike. Note that we are less than 1 picosecond time scale. An actual heat spike here is 2 picoseconds, 5 picoseconds. Now the cooling down, 7 picoseconds, 10 picoseconds, and at about 25 picoseconds, the cascade has vanished. Now we have these 3 interstitials, 3 vacancies. You see the 3 interstitials are migrating. They do sometimes go through the periodic boundaries, but this particular one doesn't actually even necessarily go through them, but then finds the vacancy and you're left with perfect crystal. These timescales effect are better illustrated in this plot of this exactly the same event. This is an individual event, so these numbers would not be meaningful in a macroscopic condition, but this is a single event. But here you see the number of Frenkel pairs is the blue curve analyzed, and then the temperature in the system is the red curve and the red right-hand side scale. You see in the ballistic phase, the temperature in the system is very hot. This is because it's a finite size system, so also the average temperature is hot. Then you have the heat spike phase with lots of Frenkel pairs. Formally, these are not really Frenkel pairs. This is the liquid-like region of the heat spike, and this lasts until about 30 picoseconds. And at about 450 picoseconds, you see the temperature of the entire cell has got back to the ambient temperature of 600 kelvins. And after that, the temperature because we don't add any temperature in any way. The temperature stays at the equilibrium temperature in principle forever, but this is the thermal defect migration stage. Note that this time scale here is logarithmic and highly logarithmic. We start at 10 femtoseconds and end at 5 million femtoseconds. So the time scale changes dramatically here. And you notice that this thermal defect migration stage starts then at about this 30 picoseconds. And then you have these, first you have these 3 Frenkel pairs, then you have 2 recombinations, you have 2 Frenkel pairs, and then finally you had a single Frenkel pair which survived for about a nanosecond and then vanished. And then we were left back with perfect crystal. Well, so you saw that these defects can be mobile, and then this can of course affect the recombination. How are they mobile? Well, defect migration is actually a big topic in itself. And on this course, we say rather little about the defect migration mechanism. It's actually something which is even now a subject of new studies when DFT calculations are becoming increasingly reliable and shown that the defect migration mechanism can actually be more complicated than people were thinking a few years ago. But for simple metals, one can still summarize it in a fairly simple manner. Vacancies, almost always the vacancy migration is just that an atom jumps from one next to an empty site to an empty site. So if this was the initial empty site, you may have an atom which happens to jump there, and then you fill this empty site, so this position becomes filled. But then obviously you have an empty site here, so the vacancy has migrated in the opposite direction to the atom. Interstitials is almost always much more complicated. The best known mechanism, which is relatively simple to understand, is the Dumble-1O interstitial in FCC metals, in which case you have these Dumble which share a lattice site. In these, what happens is that one of the atoms may move towards another lattice site, push the atom in that lattice site away, and then while this one of the Dumble atoms then fill these sites. In this case, this site would become perfect, and after the migration, the Dumble would be then here. And this is actually a relatively low energy barrier because the atoms are distorted initially. So this has a low migration barrier, which means that it easily happens already at room temperature. With the vacancy migration, you need to break the bonds of this atom to the others to get here. So the vacancy migration typically has a migration energy barriers around 1 electrovolt, which means that they start happening only at around room temperature or so. This mechanism metal can easily happen at the temperature only like 30 kelvins or so. So of course this question on when are defects mobile is crucial to be able to understand and model this long time scale thermally induced effects. And well, defect mobility, as I said, it's a big topic, but in clearly the vast majority of the cases, it follows Boltzmann statistics. That is that you can describe the jump rate with some prefactor, which for a given defect is constant, and then a Boltzmann factor where you have a migration energy, and then Boltzmann's constant and T in the denominator. And here this prefactor is often written with the letter F for a frequency, or sometimes the Greek letter nu, and here F0 is the prefactor, and these are the migration energies. And this may not actually be so complicated, because for simple defects, it's easy to understand that this prefactor should be related to the lattice vibration rate, which can be estimated from the Debye metal. And in typical hard metals or ceramics, it turns out the Debye temperatures are not so different. And from the Debye model, one can derive a vibration frequency of the order of 10 to the power 13 hertz. And the physical meaning of this vibration rate is basically the average time an atom spends to migrate in a potential well. Okay, and here I have to make one thing that some people are nitpicking on this terminology. Some people say that the Dewar diffusion should be only used for equilibrium diffusion due to thermally generated defects, and any other kind of defect migration is defect motion is should be called migration. But this is something where there is no consensus on this, and many other scientists dealing with radiation just basically use these three terms as the same thing: mobility and migration and diffusion as synonyms. And this is something which personally I don't think it has any physical meaning which term you use, as long as you define what you mean by which term. And in general, the very simplest understanding of diffusion is atoms jumping around or molecules jumping around in a liquid or solid, and also these radiation-enhanced defects do jump around. So in that sense, my personal view is that it's perfectly okay to call radiation defect migration diffusion. But I just wanted to mention this because sometimes one gets criticism for using this, and then it's better to have an answer ready. Well, Arrhenius temperature, this Boltzmann factor is known as Arrhenius temperature dependence. And this is something which most of you are familiar from basic physics or chemistry studies, because this is the Boltzmann statistics, of course, is crucial in many branches of materials physics, materials science, and chemistry. So likely I've heard of this. But even if you haven't, the important thing to realize is that Arrhenius temperature dependencies can have an extremely strong dependence on temperature. And this is illustrated on the left side for migration of vacancies and interstitials in copper using one set of factors, which is probably pretty reliable. But you see here that the defect number of defect jumps per picosecond for interstitials in copper, according to this, when you go from low temperature, say 1 Kelvin to 100 kelvins, already changes by 35 orders of magnitude. So you go from 10 to the minus 25 to 10 to the 10 jumps per second. After that, this change rate pretty much saturates because this is basically saying that you jump every lattice vibration frequency when the temperature is so high that you're clearly above this migration barrier. And the same is true for vacancies, but going from 100 Kelvin to about 500 Kelvin, you have then almost as many orders of magnitude change. Well, since these plots are maybe a bit difficult to read, people very often plot these results on a so-called Arrhenius plot, where you have the x-axis as 1 over temperature or 1000 kelvins over temperature instead of the regular temperature scale, and then this temperature scale inverts. So low temperatures are low temperatures are to the right in the plot, and high temperatures are to the left in the plot. The reason people do this is that if you take an exponential Boltzmann factor in an Arrhenius plot, it will look linear. And of course, especially before computers were available, it was much easier to fit curves on a linear plot, linear looking scale, and so on. But there is a practical consequence of this fact that there is some temperature interval where this very big increase in the defect jumps. And because of that, one can effectively say that there is a temperature interval when a defect becomes mobile. And this is often called the defect mobility temperature that, for instance, copper, people often say that the vacancy becomes mobile slightly above room temperature. Of course, formally it's mobile at any temperature, but this then relates to what kind of experimental setup you have that in a given the time scale that there is enough time for a significant number of vacancy terms. We will return somewhat to this defect migration later in later sections of this lecture notes in this same section 8. Well, the other crucial thing about long time scale and high doses is this damage overlap, which I already mentioned, that when you have damage overlapping with previous damage, the effects obviously become more complex and can become much more complicated than any primary damage models indicate. So, for instance, this ARC-DPA and RPA model, when there has been heavy damage overlap, essentially they become meaningless. So, for damage overlap, the key important thing to know is that elemental metals behave very differently from most other materials. That is, in elemental metals, damage saturates. Even if you keep irradiating an elemental metal forever, unless you start having impurity effects, you will never get fully destroy the metal. Instead, you get saturation around 0.1% in Frenkel pairs. This 0.1 is not a very precise number; it's an order of magnitude estimate. But this is roughly the right order from many experiments. But even if damage sort of saturates, which means that you don't fully destroy the crystal, you don't destroy the crystal structure, the damage you have may become more and more complicated. And in fact, in almost all cases in metals, you start getting complex dislocation networks, and this will also be discussed in some more detail later. On the other hand, in semiconductors and many ceramics and organic materials for sure, that in most cases damage buildups would proceed until you completely destroy the crystal structure, and this is known as full amorphization, when you have no length order left and the material is an amorphous material. And there is an ion beam technique known as Rutherford backscattering channeling, which can relatively easily measure this starting from single crystals. So this has been studied quite extensively. So this damage overlap, what it means is, if you look here first on the bottom graph here, means that if you measure the amorphous fraction, which can be done from this RBS channeling technique, for instance, there are other methods which can do it, then measure the amorphous fraction as a function of dose, you, depending on system, get something like this, that you have first some increasing damage, but then at some point in most materials, the increase rate of the damage increases, and then it increases for a good while, but then the damage starts to saturate, because obviously you can't have an amorphous fraction higher than 1%. If everything is amorphous, and this is then, as you see, different materials don't behave quite the same. Sometimes you have a strong increase immediately, sometimes you have a very slow increase, which then picks up. These things are by now fairly well understood, or even very well understood in many materials. Basically, the simple explanation why different materials behave differently. In some cases, when you have pre-existing damage and a new cascade, you get more damage than during the primary damage, and that leads to then that after you start damage overlap, you start having an increased rate of increase. On the other hand, sometimes you also have the opposite effect of that damage may partially anneal pre-existing damage, which would then slow down. And these models, there are many models like the which can describe this. The direct impact basically means that you just damage a crystal, and when a new cascade it damages everything it affects, but the pre-existing damage doesn't really affect the existing damage, and then you have first a simple strong linear increase until you reach saturation. But then the other models where for instance, where you accumulate defects slowly, and then when the defect concentration starts to approach a critical level, this destabilizes the crystal, and then after a good while, you then have a very rapid decrease when the defect concentration is high enough to saturate to induce amorphization by destabilization. And then these intermediate models typically include defect stimulated, that they are a mixture of this direct impact and some sort of defect related processes. This reference here gives a good overview of different damage overlap models. To give an example of what this may look like, this is a computer simulation done in our groups around the year 2000, where we took silicon crystal and kept irradiating it with self-recoils, which corresponded to the recoil spectrum of 500 kV silicon self-irradiation. There was experimental data available for a similar irradiation condition. And when we start running this, we'll see how silicon damage builds up in silicon until amorphization. This may not be fully correct, but the amorphization doses we obtain in these kind of simulations were within a factor of 2 or so from experiments. And notice that this is molecular dynamics, which doesn't include long time scale defect mobility processes. So the fact that we got the amorphization dose within a factor of 2 with the experiments indicates that the long time scale irradiation processes are actually not so important, or certainly not dominant for understanding amorphization of silicon. Now, as you see, the single cascades introduce these small disordered zones, which were mentioned in the previous section, and rather naturally, when you keep irradiating, the damage overlaps with previous damage, and you get more and more damage, and eventually everything amorphizes. But do note that it doesn't look quite that simple. If you look very carefully, you notice sometimes defect vanishes, and this is actually through low energy recoils below 15 electrovolt, below the threshold displacement energy, by sometimes induce crystallization. So it's not enough to say that you have damage which overlaps with other damage, which like with direct impact amorphization. The real picture was more complicated than that. In fact, we counted 5 different mechanisms which were active towards amorphization from these simulations. And this image sequence is from the same set of simulations as before. This is just highlighting this circle here highlights that sometimes the damage actually vanishes. In that point, there was a damage which completely vanished due to a follow-up recoil event. So you do actually have also effects which are counter to amorphization. But anyway, what is clear is that this final stage clearly looks amorphous, and by any analysis method, when analyzes it is amorphous. And in the last part of this video, I still discuss this damage recovery, because this relates directly to the defect migration I mentioned. So the purest possible experiments on the defect migration related to irradiation defect is that you irradiate samples at a very low dose, a very low temperature. Typically, the best experiments are done at 4 Kelvin at liquid helium temperature, and then trust that there is no migration going on, then start heating it up at a constant rate and measure the defect concentrations. This has been done many times in many metals and also other materials. And in most cases, most common metals follow something which looks like this behavior here. And because of that, they have been given names which are rather non-inventive. The first stage is called stage 1, the second stage is called stage 2, third stage 3, then stage 4 and stage 5. And the names are obviously completely non-descriptive, but people at first didn't understand these, but over decades of work starting in the 60s going until the maybe 1990s, these have started to be pretty well understood in common simple metals. You also see that there is some fine structure here. This is called actually divided in stage 1a, stage 1, 2, and so on migration. And from these decades of work I mentioned, there is a good consensus that in typical metals like copper, where it's image was from and so on, stage 1 is interstitials becoming mobile. So at first you have no mobility, then some close Frenkel pairs recombine here and here, but then this main part of stage 1 is when interstitials become mobile. As I showed also in the examination, an interstitial becomes mobile, it's pretty likely it finds a vacancy, recombines, and when it does that, the damage goes away. So because of that, this interstitial migration is actually very efficient and can reduce like 80% of the initial primary damage. Then there is a stage 2 which looks flat but is not quite flat. There is some recombination going on, and stage 2 is considered to be small interstitial clusters, which 2 or 3 interstitials are mobile, and some are nil with vacancies, or some may migrate to the surface, and this reduces the damage level. Then stage 3 is vacancy mobility, and obviously when vacancies are mobile, this will enhance the annealing, and they can anneal with interstitials or form vacancy clusters. And then you have stage 4, where vacancy clusters become mobile to anneal or cluster to form big vacancies. And after these 4 stages, all interstitials are gone, and the vacancies have all formed big vacancy clusters which are not mobile. But finally, at some temperatures, the vacancy cluster starts to emit single free vacancies, which at that temperature already are highly mobile and anneal with interstitials. Well, there shouldn't be any interstitial left, but maybe dislocation loops, or anneal at the surface or a grain boundary, and eventually you have no defects left, or at least not any more than large-scale dislocations, which may have been present in the sample already initially. So to summarize, you see that really in these plots that after stage 5 we have recovered to perfect crystal, and in copper this stage 5 is around 500 Kelvin. So at 600 Kelvin, by heating a copper sample after irradiation 600 Kelvin, in principle one should get rid of all defects. But this is true if the doses are low. If the doses are high, one probably gets more complicated damage, and then it's not true anymore. So for these processes, one can actually use this Kroger-Wink defect notation to symbolize what's happening. So the simple process of interstitial vacancy between each other at annihilating can be written as I plus V equals 0, that is, no defect is left. But this is not actually automatically true. In silicon, it's possible that an interstitial vacancy, when they come close by, form an IV pair, which is still a defect. And in graphene, the interstitial vacancy mobility can meeting each other can form a stone-Wales defect, and so on. The IV pair by itself is not very stable. It vanishes around room temperature. In graphene, on the other, stone-Wales defect is extremely stable and very difficult to remove. So sometimes one can have alternative reactions to this one. But then these clustering processes have a pretty obvious notation. If you have 2 interstitials meeting, you form an I2. If you have an interstitial meeting I2, you form an I3. 7 vacancy, and at 4 vacancy meeting each other, you form an 11 vacancy, and so on. And similarly, you can also, these interstitial vacancy migration processes, you can meeting processes you can form like that. So if an interstitial meets by a tri-vacancy, it gets absorbed in a tri-vacancy or left with a divacancy, and so on and so on. But finally, you can also have these defect emission processes written in these notations. You can say a V25 becomes a V24 plus a V vacancy. And you can include sinks in this. Sink is then something more complicated, say a nanocluster or a grain boundary, which can absorb defects. They are often considered to be infinite sinks, that a sink can absorb any number of defects. So then the reaction would be simply that interstitial going into a sink gets absorbed in the sink and you're only left with the sink. And you can also extend this to impurity notation, for impurities, you can, for instance, an interstitial meeting a carbon impurity would form an IC complex, more complicated defects. And one of the reasons I wrote out this notation is that in modern kinetic Monte Carlo and rate theory simulations, it's actually quite useful to have these. In kinetic Monte Carlo, one can, in the most advanced volleys, all of these are individually described and tabulated, and it's quite handy to have this notation to describe the different defect reaction processes. Well, also one thing to mention is that the defect reactions are typically considered to be instantaneous. That is, when the interstitial and vacancy or something else come within some radius of each other, they are considered to immediately meet. This instantaneous, of course, physically not quite true, but simulations show that if an interstitial and vacancy, for instance, come within 3 angstrom of each other, it typically takes only like a picosecond until they annihilate, or maybe for a stone wheels defect. If you are discussing nanosecond or millisecond defect migration time scales, this 1 picosecond annihilation time is completely insignificant. So this is a pretty good approximation. The D-trapping, on the other hand, is definitely not instantaneous because it has some probability, and the atom needs to overcome a barrier, and this barrier kind of often can be described with a thermally activated Arrhenius-like process. And one can understand this asymmetry by looking at the potential energy landscape curve. So if you have 2 defects coming next to each other, to D-trap, you need to get from a deep potential well up to the migration well. So this would be the defect migration well, and this here can activation energy for deep trapping can and often is several electrovolts, whereas the migration energy may be only 0.1, 0.2 electrovolts. So there is a big difference in this. It's quite obvious just from a potential energy view that getting over this barrier obviously must need much more time than the migration. And in the opposite process, if you have them this close by, if they do the last migration step here, then it's pretty obvious that this reaction will just collapse to the bottom of this barrier well and form a pretty stable defect. And this concludes the first part of the videos of this section 8. And after this, we'll start discussing these rate equations, which I already hinted at is one way of describing these reactions. Later on, then kinetic Monte Carlo, which is another way.